Right, good time of day, everyone, and welcome to this new MLIR open meeting. Today we have Kevin and Ting who's presenting about PyDSL. So Kevin, take it away.
All right, thank you. Yeah, my name is Kevin. I am a intern student at Huawei. I'm doing like a full-time project, and for the past 3 months, we began like working on a project called PyDSL. The company has an interest in writing MLIR in a domain-specific manner, and we're like prototyping different languages on what's the most effective way to do that. And the solution me and Ting has come up with is a Python subset that hopefully yields a pretty good MLIR programming experience for at least some of the dialects, such as affine and SCF and transform. On the right of the slide is an example code of something that does compile properly with the compiler. It is a strict subset. Python can understand this, and it's also strictly typed, which means all the variables does have annotations that are mandatory, that are required. Next slide. Yeah. So why are we doing this? Like I said, like one of the reasons because MLIR is very verbose. I believe that it's not meant to be used for programming like end user programming purposes. Even module compiler engineers complain about that like writing a large amount of MLIR code by hand can be very difficult. MLIR is I think like MLIR is a compiler front end output. And we also experimented with MLIR's Python binding, but we also find that to be very verbose and think that it's like meant to be used by compiler engineers and not the end user as well. So we believe that we need to come up with a custom solution that is closer to more idiomatic to what Python is. There is a comparison here, just a quick comparison between one they're trying out in Python and it's the output that is emitted. And while the Python code is a lot longer, it does consume a lot of return and empty spaces between codes, but ultimately it's way shorter, I believe. Use arrows. So there are some existing work that are similar to what we're doing. One of the most prominent examples is probably Mojo. It is closed source as of now, therefore, so we have to come up with our own solution. The organization does have a pretty strict requirement on what we are allowed to use as software dependencies. So we have to create our own work. But some of the features that we think like are pretty useful to learn from is like it has a bring your own dialect system, which we couldn't get around to as of now, but I think that's very interesting. And there are some other things that we think it's not great for our use case. For one thing, it's also a superset of Python, and it contains non-standard keywords like struct and var. We want to try to stick to as like a subset of Python if we can. Yeah, another example that we have come across is the MLIR Python util. I believe it used to be called Nelly, and it's created by at least created by the same author as Nelly. In the author's own word, it is not a compiler. It's simply it's simply like the existing Python binding library with more syntactical sugar, such as having additional annotations as well as type hinting, but it is not a compiler, and it relies on Python's own runtime behavior. For example, when you're defining a new constant, you do require to use the constant function, otherwise it wouldn't work. We try to avoid things like that as well and try to make our program as close to the core Python syntax as possible. Another issue is that it doesn't yet support the affine dialect, but we do need it in our organization, so it's not a good fit for us either. A recent development, I think, came out in what is going on? Oh, laser pointer. Okay. A recent development, I think this one's presented at the LLVM 2023 conference, is MLL. It's also aims to create like a Pythonic a domain-specific language, and it also, similar to Mojo, also promises a bring your own dialect system where you can create your own dialect and use it in their program. While it is Pythonic, it's also like a C. It also has like C-like syntax. It's still kind of different from Python. And of course, it's not a superset of Python either. So that does not work out for us. So our goal is to create a language that's similar to like idiomatic Python as possible. Don't have like, we don't want like any nested functions or things like that. We also wanted to support the arith, SEF, func, memref, affine, and transform dialects. We also want to have functions that are dedicated to sequentially transform the payload function that we have written. We also wanted to have at least preliminary support for compiling and calling the function directly. And as a result of Python's dynamic nature, we also require static typing. That's just to keep the compiler simple for now. Dynamic typing is very difficult to transform into MLIR. Yeah. Is there any questions so far, or can I continue? All right. So now I'm going to show you like a behind the scenes, like what is going on, a rough overview of what the compiler is doing. And for that, I created this dummy, a really simple dummy program that I'm going to walk through. Some of the variables are not exactly used, but I'm just here for demonstration purpose, like memref 64. That's a type that's generated from memref factory, but those are not used. I'm just we'll see later why I included those. One thing of note is that not everything here is actually compiled. Part of this program, starting from here to here, is actually run by the Python. It's part of Python's runtime, but Python's runtime never touches these code. These code are only compiled; they're never run. And the program and this function that's responsible for kickstarting that process is the compile function. It's this compile annotation, which takes in this function and pass it through to the compiler. One of the things, because there's this two areas, this Python runtime and the runtime that's being compiled. There needs to be a bridge, and this bridge is the locals function. This is a built-in Python function that grabs all the local variable defined so far and have it as a dictionary, seen here. This is very important because this is the part where we define all the types that we're going to be using in the program, and we also have a custom range function that's going to override Python's default range function, and these are all included in a Python dictionary that the compiler will use. So the first step of this compilation is the parser. And luckily for us, Python already has a library that lets us parse Python into a tree. It's called the AST library. We start off by using inspect.getSource to convert the function into a string representation of this program. And then we use AST to parse. And here is the dump to illustrate what it looks like. This is very complicated, and there's a lot of stuff that we're never going to use, such as KW default. We're not going to be using any of those. So I'm just going to simplify into this tree view. One thing of note is that all the green nodes in here represent variable creation, and all the orange variables are nodes are those that requires those variables to be used. Yeah, so we start off by using a visitor to visit the module node at the top of the tree. This top of the tree basically pushes the locals function that we have in the locals dictionary we have initialized earlier onto this variable stack. And after that, we visit the function def, which is Python's function node. This kicks off a process that creates a func op, and in turn also pushes a new block onto the stack with the arguments A and B defined as func op parameter values. These are mapped to these Python variables on the stack. After that, we start walking through the body. We first initialize a D variable of type F32 and L of type index. In order to know what these types are, we refer to the locals function that we have, the results of the local function that we called earlier. These include those types that we have imported. These are classes that basically describe what sort of values needs to be created. And in our case, we create a const op 5 with a type of index and const op 12.5 with type F32. And these are in turn connected to these variables, which are pushed onto the stack. And from now on, we're just going to draw these blue arrows just to illustrate that this is what the variable is referring to. After that, we look at we walk towards the for loop, and we look at its iterator variables as well as the list of ranges calling. The range is a special function that's basically a sort of macro that takes in the for node and transform it into its respective MLIR operator. In our case, this is a for op, and it will also look at the start, which is 0, the stop, which is const op 5, which comes from this L, and we look at the L, and it shows us that we need to use const op 5. The step is 1 by default. We didn't specify anything, so it just defaults to 1. And all this is being referred to. The iterator variable is being referred to by I instead of this new block that we created for the for loop. We just iterate through the body. The E, very similar process that we have seen earlier, so I'm just going to skip that. And here is our first binary operator. The binary operator uses a system that we have created recently, where it first traverses to E and D, grab those variables that they're referring to, and look at what operator they should be using. In our case, we're using the add op. The green and yellow arrow identifies what ops E and D I'm pointing to, and they each respectively points to 3 and 12.5. And yeah, as such, we place those const op instead of the add op. Yeah. And the final step in this process is the return operator, and this maps to a return op, which as we know, every single function op ends on the return op, and therefore that needs to be added at the very end. The traversal of add and div, as I said earlier, we already seeing how binary operators are being traversed, so I'm going to skim past that part as well. But know that these arrows are connecting in such a way that that's already being done for us. And finally, we leave the function, and we destroy this block because it's no longer needed. And the visit function is basically done from this point on, and everything from here on is like very trivial for us. The MLIR, most of the work can be delegated to MLIR's library at this point by using a verify function to make sure that this graph is consistent, and finally converting into a string, which emits the final MLIR, which corresponds to the Python's behavior. Now, there's a couple of things that wasn't mentioned in the process that we have seen. Oh, by the way, are there any questions so far? I think it's good. No question. Okay, I'll continue. There were a couple of more specific things that wasn't mentioned earlier because they're a little bit more complex, so I'll just quickly describe them here. Affine dialect, as I described earlier, is very important for our use case. This is one of the biggest reasons why we are creating PyDSL in the first place. So we create these meta function classes. We call them meta function. I think it can also be called macro. And what they do is that these functions, they're kind of like pretending to be Python function, like affine range, affine map. But what they're really doing is that they're the compiler is passing the node that they're contained. For example, for affine range, it wants a for loop. It wants the for node, and it will try to convert the for node into its respective MLIR representation. These are not actual Python functions that are called. These are more like macros. For affine dialect, some of the macros we have to create are like affine range, affine map, the dimension, and symbol. One of the benefit of our system is that Python allows renaming on the go like this, so we can define it in a more concise manner. Like symbols can simply be defined as S and B, and they're enclosed inside of an affine range. And there's also affine map are used instead of indexing, Python indexing. So when you want to index a memref using affine map, that automatically transform into a affine.load or an affine.store. There's also the transformation dialect syntax. Like I said earlier, we want to have the ability to have a function that can transform the payload function, which is, we have an example of a payload function here. And this is a transform sequence that transforms this. And we define in the compile annotation, we include this function. We include the transform sequence, which then we can then use the match functions to match up all the operators that are being tagged by these specific Python doc string. Because we cannot annotate anything, we cannot annotate for loops in Python. This is the solution that we came up with. I think like this is a good idea as well, because these transformation technically shouldn't affect the final behavior of the program besides performance. So I think having a doc string actually kind of makes sense as well. But essentially, in this example, we are matching all these for loops and we are trying to fuse them together and finally use the tiling at the end. And this program does work, ended up working. Now, there are some challenges still. Like it's important to keep in mind that this is a very early stage project. I've only worked on this for 3 months, and there are still a lot of features that are missing. There's also inherent problem with trying to transform Python into MLIR. They're solving very different problem domains, and this is like a very non-trivial problem. For example, Python is a very defines a lot of its behavior during runtime. For example, these are all legal code. The definition and type of B is determined at runtime, and we cannot anticipate whether, depending on whether this is true or false, we cannot anticipate whether B is even defined by the time we are trying to print it here. Another example is this. In MLIR is just an iterator. It's just an iterator variable that's basically it becomes no longer relevant when we leave the for loop, but it still remains relevant in Python, because even if you leave a for loop, I doesn't get popped off the Python stack, so it's still gonna be, you can still use it. In this case, a printf for, and there's so many other issues that we could go on and on. So what we have to do effectively is just we have to restrict our compiler. We don't have a lot of time and energy to work on all these edge cases for now. So we're basically restricting our scope to a very limited subset of what's allowed and what kind of programs allowed and not allowed to be written. And to imitate the runtime behavior of Python, we would need a lot of additional static analysis and a lot generous use of yield op to deal with cases like that. And since this is not important for our use case, we're not working on any of this at the moment. Yep, this is similar to what I was saying earlier. We're just making a minimum viable product. We're just testing to make sure that this even works at all. So no duck typing, we're using strict typing, and we're only using types that we absolutely need. And these are basically the types that we need. Our focus mostly is on nested affine for loops, affine load and store, and trying to keep the compiler as simple as possible with minimal lines of code, because we need this code base to be maintainable by our organization. Yeah, just a couple of other limitations, just to nail the point. We cannot use a variable that's defined in a for loop outside of the loop. That requires yielding in MLIR. We're not going to analyze that for now. We cannot yield a variable to the next iteration, so we cannot support accumulating variables either. And affine symbols and dimensions, as we have seen earlier, has to be defined explicitly, and it's quite verbose. It's not very desirable, but that also requires analysis. So we're just going to stick with that for now. Just a couple of other issues. The compilation error message also looks ugly. It doesn't have very good programmer support, though I don't think that's hard to fix. That's definitely an issue we can get around to doing. It's just that we can't we don't really have the time to do that for now. And yeah. Okay, just to wrap things up, there's couple of things that we have been working on. I think will be pretty, well, which I think is pretty interesting and worth mentioning. One of my favorite features is the fact that once you compile the function, you can call it directly from Python. This is a program that actually prints out 20.3. That's the program that yields when you put in 25 and 3. What's going on behind the scenes that we first, using the process we have mentioned earlier, we compile it into MLIR, and then we use several lowering passes, and then use MLIR translate and clan to turn into a shared library. And then finally, we use Python's built-in CDLL library to call that shared library. And this allows us to effectively call this the shared library. Yeah. We are also trying to keep our code clean with all sort of just general good practices with polymorphism. In fact, this here is actually inspired by what I've seen on modules documentation on their types. We have these rather idiomatic operator overloading for each of the type that we have, just to make the code easier to maintain, because I think it's very undesirable to have these types, to have these behaviors defining the visitor itself. We want this code to be extensible. It's not just a one-off gig. Yeah, so that's it. Thank you so much for all your attention. And yeah, and I appreciate any feedback you guys have. I'm happy to hear it. I'll take them into consideration.
Thank you, Kevin, for the presentation. That's a very interesting walk. I may start with a quick question, like on the last slide that you presented, you're compiling to MLIR and using Clang and using a shared library, but we have the ability to use the JIT execution engine and do all of this in memory. Like I think we even have some Python examples that can do that. So I was wondering why did you go through an external .so here?
We actually looked into this. I believe Nelly uses the JIT, the just-in-time compilers, as well. We ended up doing this because we want to be able to run this on various. We want to test this on various heterogeneous architectures. We don't want there to be anything virtual going on when we're testing the performance of these programs.
What did you mean by virtual?
The just-in-time compilers, I think, is just running on in memory on top of the CPU, but we might be running this on I don't know, on a kernel code running on specific devices that we have here in our organization. So we want to be able to make it actual native code that can run anywhere.
Yeah, I can imagine that. I'm not sure how you would call this from Python though. But also the JIT in LLVM has the ability to cross-compile and remotely execute. It's just annoying to set up, but it's also possible. If there is an LLVM backend for the targets, then the execution engine can handle it in theory. But in your case, in any way, since you're loading it since you're loading the .so in the current Python process, you have to execute it for the current CPU, right?
Well, it doesn't have to lower to .so. It can lower to whatever what sort of binary that we need for the specific use case, right?
Got it.
All right, so let me try to answer this. So I think Kevin's, our goal is just to lower it into a binary. We have a separate runtime to launch it onto the device of interest. So yeah, we don't have anything just in time about this. We are just like generating a binary, and then we'll take that binary and use our internal style of dispatching that onto the actual device that we have. So that's why we did not really look into a JIT approach, because and this testing method that Kevin has is really just to test that the person who is writing the PyDSL did not make a mistake. So we lowered it onto CPU, just making sure that the person understood the PyDSL syntax and did not make a mistake, and he can compare it with a naive Python implementation to make sure it's correct, and then we'll channel it down to a different lowering pipeline for our device code generation. So that's the key purpose. But thank you for the suggestion about the JIT part.
Yeah, we could definitely make it so that you could run using JIT instead of just compiling it down to lower. And we're just doing this as our first approach because that's more desirable for our use case.
Okay, thank you. If anyone has a question online, feel free to either raise your hand or unmute yourself to.
Yeah, I don't have a raise hand button on my device. Yeah, I had the same question as Mehdi about JITting. Yeah, I guess. Oh, you can do fun stuff with libraries, but I have a different one. You mentioned transform dialect in the beginning, and I haven't seen any transform dialect Python binding something in the slides. Is it somehow connected here? Is it a completely separate thing? Do you have like a separate API? Just wondering.
There was a slide with match and stuff like this.
Oh, I think it's worth mentioning what the tag and annotation is doing here. Tag is actually just a regular function, not regular function, it's a macro, but but tag is just like all these like a range or am. You could actually just like tag maybe like a, and it will basically tag this this const op. We have to do it like this. What this annotation with instead of a docstring is doing is it's taking the for op as the second argument of this tag function. But since we cannot have a for loop as an argument in a Python function, this is what we ended up doing.
I think the question is, in your implementation, you use the Python binding in MLIR for affine, for example. You want to generate a affine.4. How are you using the transforms Python binding?
Oh, the transform is just part of the MLIR Python binding. They're all part of the same library.
Okay, so the answer is yes. Okay.
And that specific thing, does it go through like an attribute on?
Oh, yeah. I'm not sure. I think you're talking about the fact that this gets tagged with a unit attribute.
I'm just trying to understand how it's set up. Like there are multiple people who have set up various things for transform dialect in Python. I'm trying to see if it's the same with a different syntax. Is it completely different? Is it something that we want to put upstream? So yeah, my specific question here is like, how does it? I see match targ fuse 1. And how does it look in the MLIR? Like when you run the transform interpreter, what does it actually look for?
Oh, maybe it's I don't have the generated output for this on my hand on the slide deck. But essentially, what transform sequence is doing is it's just creating additional like MLIR code that's beneath the payload. It's just another function. I don't have an example for this on the slide deck, but this is written in pretty much just.
I think your first page has it.
A
very small picture.
There is a very small picture of what it generates here. Can you blow it up? It is so small though. I can't fit it on the slide.
No worries.
But this is actually the same program as you've seen with that example.
I understand how it can be done. I'm just wondering if you have found another way or not, and it sounds like you have not, which is like, you just put an attribute on the affine.4 operation, and then the match op is just looking for that specific attribute. Which, I mean, we can also take that offline. I don't want to waste a lot of time here.
I don't understand the question.
No, the question is if you add a tag on for the match, right, which is matching that for, how does that translate into the match in the transform dialect?
That is very simple. The only thing that tag is doing is adding a unit attribute to
that's what I said.
That's all it's doing. It's not doing anything else. All the remaining match and I think tiling, those are all just standard MLIR operation, transform operations. I'm not sure if I answered your question.
Yeah, it does.
Okay.
Thank you.
Yeah. Is there any other question? Oh, there's a few in the chat.
Oh, in the chat.
Okay.
Yes.
Are you using MLIR Python binding to emit the MLIR? Yes, that's part of our software dependency.
Okay, scroll down. Yes.
AOT first makes a lot of sense to me. Going straight to JIT makes it easy to create a lot of enantic? Anticipated coupling.
Yes, agreed. Yes. We have not open sourced yet, but we do plan to. And excuse us for using the wrong template. It says confidential, but it's not confidential.
Yeah, this is public work. We do plan to make it public, and hopefully other people can benefit from this work as well.
That's right. We forgot to delete the confidential on the standard template. But rest assured that we are open sourcing it.
Yeah, that's all the questions so far. If there's
any more questions?
I think I probably can just do one out of curiosity. And thank you for the presentation. And I mean, I definitely agree. You know, MLIR is an IR, it's not a language. So, you know, we need the languages to write it. I'm sort of wondering with respect to, we mentioned like the different dialects. How easy is it actually to, you know, be able to customize some of the behavior? So I mean, like if I look at the current lowering, you know, it's relatively concise, and it's you know, at the Python side, you know, because it sort of assumes some of the lowerings, right? It's if you do this one, it's this affine, etc., etc. For folks that want to be able to like mix and match this with different abstractions or dialects, do you have any idea of, you know, how difficult it would be, like symbol wise, expression wise, how easy it would be to extend that?
Yeah, so this is one of our goals. We want to make this as extensible as possible. One of the ways we are already doing this is using by defining like query defined classes where you can where you can just basically extend those classes. Let's just like give a concrete example. For example, for this class, I believe this is implementing a float. If you want to, for example, one of the first steps you do have to do is that you do have to support the MLIR. Your dialect does have to support the MLIR Python binding first. That shouldn't be too hard to do. We had to do that for like affine dialect. That wasn't that wasn't the upstream when we started work on this. All we had to do is add a .td file to a CMake file in order to make that work. I had to define a couple of like custom functions in the Python binding for affine, because the auto-generated code didn't really work out for us. So there is that process can be like depending on how familiar with that part of the process, it could be potentially complicated depending on your dialect. But after that, this is within this layer, we try to make it as easy as possible to like implement additional dialects that already exist in the MLIR Python binding. In this case, we have a lower function for every one of our type, which effectively what's doing is returning a value. This is actually outdated. It's no longer up view. For example, this float, depending on, for example, if this float came from a function, it will lower that to its respective representation in MLIR Python binding. In that case, I believe it's called like argument value class or something similar to that. If it came from a const op, it will just return the value returned by the const op. And similarly, you can obviously create your own dialect, and you could create your own class with a lowering function that lowers to your Python binding class that you have binding to your dialect. In terms of those other functions, that's in terms of type. But in terms of operators, I try to use a system. The prototype name for it is meta class. I don't think that's the right name, but I think it should be called macro or something similar to that. But let me try to find the slide where I talked about this. Oh, that's good enough.
Yeah, so I think the summary is it should be pretty extensible if your dialect has a proper Python binding to interface with the PyDSL tool. The goal of this tool is meant to be extremely thin and lightweight, and because it served a particular purpose for our project, it's just just to ease people's life so they don't have to handwrite the MLIR text. But yeah, it should be, how many lines of code is that? It's like
it is getting kind of large because there is a handful of abstractions I have to create, but I still say it's fairly lightweight. Like I still think there's less lines compared to Nelly.
Don't compare that, but yes, it's very small. Yeah, we hope to upstream and open source it in a very short time, and definitely feel free to visit. We'll post it somewhere. The link to have a link yet.
Awesome. Thank you very much.
I got a question. Is there still time? Yeah, there's still time. Can you go back to the slide with the double underscore add and all that stuff where you were talking about you got the idea from Mojo? Yeah, that one. Yeah, how does this work? What's going on here on the right hand side?
On the right hand side, this is basically just a Python class. It's currently part of the compiler. Yeah.
But so I get it. You have some class where a plus b calls double underscore add, but
yeah,
and it's inside your compiler. It's inside your compiler, which means like if you're if I'm just trying to understand where in your compiler you're actually performing the a plus b.
Let me go back to here. I think this. Let me go back to the add.
Yeah. Okay. So yeah. So you have essentially an evaluator for an addition expression, right?
Mm-hmm. Yeah. Sorry.
So if you go back, so does that mean that those double unders, those dunders, are only for arithmetic operations?
What I'm trying to do is just keep it as close to Python standards possible. I started off by creating like additional dunder functions, but I don't think that's a good idea. I just want to, because dunder functions are reserved to Python's language specification. I don't want to pollute the namespace there. So we just
what I'm saying is you're only using these whatever the class is called on the right. I don't know what it's called because there's no class.
In this case, it's a float class.
Okay. So it's, okay. And so you're only using this because it's kind of like an interpreter, small expression interpreter. You're only using it for evaluating arithmetic expressions. That's what I'm trying to figure out.
There are actually a couple of other use cases. For memref, it also uses, I forgot what it's called, get item, I believe, get item and set item dunder function as well. Yeah. Just try to. Sorry.
Yeah. So sorry to interrupt you. Yeah. So this is what I was trying to figure out. Like, it looks like you have a little interpreter inside of your compiler, right? Because you're like interpreting, well, memref square brackets. right? So I have a memref. I'm gonna get an item. I'm gonna index into the item. I'm gonna index into the memref. And if you're doing this inside your compiler, that means you're looking at an AST expression or whatever, and then you're like, what does this evaluate to, or what can this be interpreted as? That's what I was trying to figure out. So I think the answer is yes.
By square, whenever the compiler sees a square bracket followed by any variable, no matter what it is, it will try to call. It will first try to get the type of that variable, and then it will try to call the dunder function called get item or set item if it's depending on the context.
Yeah, cool.
Oh, that's Max. Hello.
Oh,
That's Nelly author.
That's Nelly author. I didn't even notice.
Yeah, we study your work, by the way.
Yeah. I will get your work very much.
Thank you. Yeah, thank you. Yeah, thank you for the answer. Nice presentation.
All right, thank you. Is there any other question? Oh, there's
It's comments like they actually did a DSL.
Oh,
really?
we did a work. Oh, we should take a look.
We did a work in 2016 DSL transform C++ program with affine. We published this title, programmable.
Yeah, let's check out the paper.
Formally verified.
Yeah, thank you, Nimit. We'll check out your publication.
Is there anything else? Let's see. I'm not referring to what the methodology. I think it's just people talking to each other.
And there was more question on the chat so far. I was just checking. So that's it. If anyone else online wants to follow up with the other question, please unmute yourself or ask in the chat. We can repeat it.
Is there something that I missed in the?
No, that's it. Yeah. Thank you to everyone for joining and giving us good suggestions.
This was like, there's a lot of very good questions that was asked. I will definitely take all these into consideration, including the JIT suggestion.
All right. Well, I guess we can leave it there. Then, if there is not more question, thank you for sharing this walk with the community. It was very interesting. Please send me the slides, Kevin.
Yeah,
so
I'll do it.
All of it. And see you next time.
Bye.
Happy holidays. Thanks.
Thank you.